So in this section, we're going to talk about some algebraic operations about matrices. So basically, we learned that we can write matrices in terms of column vectors. And if you expand, or if you write all the entries of the column vectors, then we get A equals to this large matrix. Or simply, we can abbreviate this with A sub ij with square bracket. Here, the ith row of the jth column is denoted by A sub ij, and these things are called as the diagonal entries. A diagonal matrix is a square matrix that consists of the diagonal entries, which means all the non-diagonal entries are 0. So for example, all the identity matrices are diagonal matrix. So for example, I sub 1 is just 1, and I sub 2 equals to 1, 0, 0, 1, and I sub 3 equals to 1, 0, 0, 0, 1, 0, 0, 0, 1, and so on. So here you can see that only the diagonal entries are survive, and all the others are 0. And also, like, if you have a matrix which is given by 1, 0, 0, 0, 2, 0, and 0, 0, negative 5, well, this is also a diagonal matrix because the only non-zero terms are at diagonal. A zero matrix is n by n matrix, with its entries are all equals to 0. And we're going to write zero matrix as just like 0 like this. And there's no restrictions for zero matrix. So for example, like this 3 by 2 matrix that consisting of 0 entries is zero matrix. And also this one is zero matrix. And whatever matrices that has 0 entries are considered as the zero matrix. Two matrices A and B are equal if they are the same size with the same corresponding entries in each columns. So for example, suppose that A is given by 2, 1, 3, 4, 5, and 6. Then A is the same as B if and only if B is given by 2, 1, 3, 4, 5, and 6. So B should be the same size as A with the same entries in each column. If you have two different matrices with the same size, the addition of matrices is just the addition of each entries. So for example, if A is given in this way and B is this one, then A plus B should be 2 minus 1, 1 plus 0, 3 plus 10, 4 plus 9, 5 minus 8, 6 plus 5, which will give you 1, 1, 13, negative 5, negative 3, and 11. And you can also multiply the given matrix by any scalars. And when you multiply the scalar into the matrix, then you have to multiply the scalar into each entries. So for example, if A is given by this and R equals to 5, then 5 times A is 5 times 1, 5, 9, 2, negative 4, and negative 7, which gives you 5, 25, 45, 10, negative 20, and negative 35. And there are several properties of matrix addition and scalar multiplication. So suppose you have A and B and C as matrices with the same size and R and S be scalars, then A plus B equals to B plus A, and we call this as the additive commutativity. And we also have additive associativity, which gives you A plus B plus C equals to A plus B plus C. And if you add zero matrix to a matrix, you get A itself. So we call 0 as the additive identity. And you can also distribute scalar into matrices or matrices into scalars, which means like R times A plus B equals to RA plus RB, and R plus S times A equals to RA plus SA. So we call these two properties as distributivity, and R times SA certainly equals to RS times A, and this is called as the associativity in multiplication. Okay, now we want to define the matrix multiplication, And matrix multiplication can be defined as the function composition. So remember that the matrix vector products is defined as the linear transformation. So suppose that you have a matrix B and you multiply B into X. Then this B maps X into some different places or different space. Then that gives you B times X. And then if you apply A to BX, then this will map BX into A times BX, where simply we can tell that this point has to be AB times the vector X. So for example, suppose that B rotates X by 45 degrees, and let's say A dilate its input by a factor of 5, then ABX gives you, so you first want to apply B into X, that rotate X by 45 degrees, and you stretch that vector by a factor of 5. So intuitively, you can think that the composition of function is like layering of the given transformations. So let's talk about algebraic definition of the matrix multiplication. So suppose that A is given by n by n matrix, and B is an n by p matrix with its columns b sub 1 through b sub p. Then the product AB is given by m by p matrix whose columns are AB1 through ABP. So here, to be able to multiply two different matrices, we need to match the size of the matrices, which means like A is given by m by n matrix, and B is n by p matrix. Then the number of columns of A has to be the same as the number of rows of B. And then the result becomes m by p. That corresponds to this m and that p. So let's practice to calculate the matrix multiplication. So suppose that A is given by 3 by 2 matrix and B is 2 by 4 matrix. Then we can expect that, well, AB should be, so if you erase these two here, then we get 3 by 4 matrix. So let's pause the video and try out this exercise. Okay, so let's solve this problem together. So basically, by definition, A times B equals to A times the first column of B, which is 1, negative 2, and A times 2, 3, and A times 0, 1, and A times negative 4, 5. So first of all, the first column, A times 1, negative 2, which is given by 1, 3, negative 4, 5, 0, 2, times 1 and negative 2. And we know that this equals to 1 plus 3 times negative 2, negative 4 plus 5 times negative 2, and 0 plus 2 times negative 2. That gives you negative 5, negative 14, and negative 4. So if you do the same calculation for the other columns, then you will get the result as follows. So if we cook up a matrix using these vectors as columns, then we get AB equals to negative 5, negative 14, negative 4, 11, 7, and 6, and 3, 5, and 2, and 11, 41, and 10. So in the previous example, we've seen that we can calculate the matrix product AB by working on the column vectors, but also we can calculate the same thing component-wisely. So for example, if the product AB is defined, then the entry in ith row and jth column of AB can be calculated by taking the product of ith row of A and jth column of B. So what it means is, suppose that you have two matrices, say this one to be A and this one to be B, and this is AB. So let's say you want to find ij entry of AB, so this to be ith row and that to be jth column. Then what this equation means is that, well, you just take off the ith row of A and the jth column of B, and then you take the dot product of these two vectors. So let's practice the calculation using the following example. So suppose that A is given by this matrix and B is that one. Then we can calculate AB, which equals to 0, -4, 9, 2 times 1, -1, 2, 3, 3, and -4. So here we know that A is 2 by 2 matrix and B is 2 by 3 matrix. So number one, we have these two numbers matched each other, so we can take the matrix product. And number two, the resulting matrix should be the rest of the thing. So it should be 2 by 3 matrix. Therefore, AB has 6 entries, and we want to fill in these 6 different blanks. So for the first blank, say this one, so it is located at the first row and the first column, so which means we want to take the dot product of the first row of A and the first column of B. So AB11 equals to 0 times 1 plus -4 times 3, which will give you -12. And also, if you want to fill in other blanks, like say AB, 1, 2, then this corresponds to the first row and the second column of AB. So you want to take the dot product of the first row of A and the second column of B. So that gives you 0 times -1 plus -4 times 3, which gives you again -12 as well. So if you do this for each entries, then we get AB equals to -12, -12, 16, and 15, and -3 and 10. Okay, so you probably want to calculate by yourself. So let's pause the video again and try to calculate the given matrix product. Okay, so did you figure this problem out? Well, let's solve this problem together. So basically we have 3 by 2 matrix times 2 by 2 matrix. So we can tell that the result should be 3 by 2 matrix. So we want to fill in 6 different entries. So at the first row, first column, you want to take the dot product with this one and that one. That gives you 1 times 4 plus -2 times -2. And for the 1, 2 entry, we take the dot product with this one and that one, which will give you 1 times 7 plus -2 times 1. And like the same argument, well, we get 3 times 4 plus 5 times -2. And for this one, we got 3 times 7 plus 5 times 1. And for the last row, we have 0 times 4 plus -6 times -2 and 0 times 7. And finally, we got 0 times 7 plus -6 times 1. So if you calculate all the entries, 8, 5, 2, and 26, and 12, and 6. So the pros of this calculation is, well, it looks like it's shorter than working with the column vectors. There are several algebraic properties of matrix multiplication, and this time, these properties are really important. So suppose that you have A and B and C to be matrices, and R be a scalar, then certainly we have the associativity in multiplication. So A times BC is the same as AB times C. So we call this as associativity. And we can distribute matrices in each other. So A times B plus C is the same as AB plus AC. B plus C times A is the same as BA plus CA. And we can pull scalars into the matrix product. That means R times AB is the same as A times RB. So it's associativity plus commutativity. And we always have the identity matrix. That gives you I sub m times A equals to A. So basically, commutativity in multiplication does not hold when you multiply matrices. So if you look at warnings down here, so in general, matrix multiplication is not commutative, which means in general, AB is not equals to BA. Also, cancellation does not hold. Suppose that you have AB equals to AC, then this does not always mean that your matrices B and C are the same. So using this fact, even though you have AB equals to 0, well, that doesn't mean you can cancel out A or B. So AB is 0 does not always imply either A or B equals to 0. And lastly, if the given matrix is n by n square matrix, then we can certainly take the power of the given matrix. And we denote A to the k as the k number of multiplication of the given matrix A. And A to the 0 equals to the identity matrix. So let me give you some counterexamples about the above quotients. So the first example is, so suppose that you have A equals to 2, 3, negative 1, negative 3 half, and B equals to 3, negative 1, and 6, negative 2, 2/3, and negative 4. Then if you calculate A times B, then you will get all the entries equals to 0. However, note that both A and B's is not equal to 0. Also, suppose that A is given by 1, 2, 3, 4, and B is 5, 6, 7, 8. Then if you calculate AB and BA and compare each other, then AB equals to, I guess, 19, 22, 43, and 50. And BA equals to 23, 34, 31, and 46. And you can see that these two matrices are not the same. So this is a counterexample about AB is not equals to BA. The transpose matrix of the given matrix is a matrix you switch the columns into rows. So for example, like if A is given by A, B, and C, and D, A transpose is defined as, so you write the column into rows, so that equals to A, C, and B, and D. Also for B, we switch the column into row, that gives you B transpose, the same as negative 5, 1, 0, and 2, negative 3, and 4. And lastly, for the matrix C, C transpose equals to 1, negative 3, 1, 5, 1, negative 2, and 1, 7. So there are several properties about transposing matrices. So suppose that you have matrices A and B, then A transpose transposes that is you're switching rows and column, and then switching that again, which will restore the original matrix. So A transpose transpose equals to the original matrix A. And A plus B whole transpose is the same as, well, we can first transpose the matrices and then add them together. And for any scalar R times A transpose is the same as R times A transpose. And AB transpose is the same as B transpose times A transpose. So this property, the part D, is very important. So note that the transpose of the product of matrix equals to the product of their transpose in reverse order. So let's look at the following example to see whether we really have to take the reverse order or not. So let's pause the video and try out the part A and part B of this exercise before I give you the solution. Okay, so let's solve these problems together. So basically, A times B is given by 1, 2, 0, negative 5, 3, and negative 1 times negative 6, 1, 2, 4, 3, and 0. So if you calculate this component-wisely or entry-wisely, then that gives you, I guess, negative 6 plus 8, 1 plus 6, and 2, negative 20, and negative 15, and 0, and negative 18 minus 4, 3 minus 3, and 6. And that will give you 2, 7, 2, negative 20, negative 15, and 0, and negative 22, 0, and 6. So if you transpose this matrix, then you will simply reverse the rows and column, which will give you 2, negative 20, negative 22, 7, negative 15, and 0, 2, 0, 6. So let's verify that this matrix AB transpose is really equals to B transpose times A transpose. So here we have B transpose equals to, so if you reverse the rows and column, then you will get negative 6, 4, 1, 3, 2, 0. And A transpose equals to 103, 2, negative 5, and negative 1. So B transpose, A transpose, well, this is the same as negative 6, 4, 1, 3, 2, 0, multiplied by 103, 2, negative 5, negative 1. This will give you negative 6 plus 8, and I guess negative 20, negative 18 minus 4, 1 plus 6, negative 15, 3 minus 3, 2, 0, and 6, which will end up, well, I guess 2, negative 20, negative 22, 7, negative 15, and 0, and 2, 0, 6. So we get the same matrix. So here, the point is, so here, note that B transpose is 3 by 2 matrix, and A transpose is 2 by 3 matrix. So if you calculate B transpose, A transpose, so if you kill the intermediate numbers, then the result should be 3 by 3 matrix. However, if you calculate A transpose, B transpose, then this is 2 by 3 matrix times 3 by 2 matrix, and you're gonna get 2 by 2 matrix as an answer. So because AB transpose is 3 by 3 matrix, the second one never equals to the A times B transpose.